Record button, going to Discord, changing my scene. And if you notice, we're going to start with transmit path. We start with a baseband assembly. Now, for those of you that like to follow along with using the C's and D's, great. Highly suggest you write everything in there. If not, come back, take a look at this recording. I am recording it, thank goodness. You guys are wonderful out there. I'm getting, your homework in. So after we go over homework, I'm going to ask for it about an hour later to give you that technical glitch issue worked out. So if you've already got them, some of you have already been turning them in. Good for you. Appreciate that. Been going through them quickly just to see where the possible issues might be. And everybody's doing pretty good. So we're going to start with the baseband assembly. Now, I'm going to keep coming back to this particular picture just so I can blow up the front panel here to point out where these items are when we get to them. We're going to start, I think it's on page 4, bottom right-hand side. It'll say transmit baseband. At the bottom. We're going to start at the bottom right hand side. You can see where we've already got the attenuator marked out, but I want to highlight that mission traffic area. This is outside on a connector. Actually, there's a couple connectors that it's a Canon plug, probably about 50-60 pins in it. Maybe 100. It's been a while since I've taken a look at it. And that's where the multiplexer is going to come in at. It's going to send that aggregate into the back of the baseband assembly, and the first place we're going to go to is the attenuator. Now, before we go any further, let's take a look at where that attenuator is. You see the middle section right here where we have the receiver baseband. It'll say RCVR at the bottom, right above that black plastic piece. And then it'll have 4 lights. And then right above that is your receiver baseband. Now, that is for the receive. Off to the left of it is your transmitter baseband, and that's where we're at. You'll notice that the differences between the receiver attenuator versus the transmitter receiver or attenuator is different. We actually have 2 knobs here. The top knob, which is the 0, 10, 20, means that you can go all the way up to 20 without too much of an issue. Just to show you, I was not able to type in anything in chat. Uh-oh, that's not good. Okay, just keep us updated. The second part is you'll see that the knob underneath the 0, 10, 20 is a 0 through 10. So let me try to explain this to you. If I wanted to put in 15 dB of attenuation, I'm going to go to the top knob, I'm going to select 10. I'm going to come down to the bottom knob, and I'm going to click over to 5. That gives me 15. So those two work in cahoots with each other. And if you wanted to get 30 dB of attenuation, the top knob would have to be on 10. The bottom knob would have to be on 10 also. That gives you 30. I'm going to keep that blown up there. And this is what you're going to see. You got 0 to 30 dB of attenuation with the 2 knobs. The idea is to get it to 3 volts peak to peak. Where are you going to view the 3 volts peak to peak, and knowing how it's going to, or if you know where to find it on the front panel? Well, let's go back to the front panel here. How do I know that I'm going to get 3 volts peak to peak? Let's take a look at the far left-hand side of our meter. Wow, a meter. You'll notice it has some green in it. I hope everybody can see that. You have to put it on transmit baseband, and the needle should be in the green. if it is not in the green, then you got to come over to the transmitter assembly and, excuse me, LRU, and attenuate using those two knobs to get it into the green. Now, more than likely, when you guys get to doing the tisser tomorrow, it's already going to be in the green because there's no multiplexer that's tied to it. When we were able to put the FCC 100s up to it, we were able to do that. We could use the attenuators to either turn it down or turn it up. So that's how we get that 30 dB of attenuation, and we can tell the 3 volts peak to peak on it. Most of the time you're going to have to vary it because you have a short cable between the multiplexer and the baseband assembly. Remember, the shorter the cable is, the more attenuation you're probably going to have to use. We're going to look at next is called the baseband filter. This is a notch filter. What does that mean? It means that we are going to clean up anything in the 8.5 megahertz area. In other words, nothing that is at the 8.5 megahertz is going to get in here. But let's go back to the transmission traffic, which is back here right before it hits the attenuator. The idea behind this is you're going to have two different types of traffic coming in here. You're going to have CDI, and then you're going to have pseudo NRZ. Whichever one it is, that's where it's going to be coming in at. So when it gets to the summing buffer amplifier, you can see the types of traffic that we have here. You got 72 to 4608 kilobits per second, which is the CDI, and the 6144 kbps is pseudo NRZ. Now the 8.5 megahertz is a subcarrier that we're going to combine with it. Now this summing buffer amplifier, if you read back in the old Dolan Hall area, where we talked about what's called I think it's a common base amplifier, and it's going to take two signals in, and the output is going to be on the base portion, and the particular transistor has a unity of 1. In other words, it can take two signals. If one's stronger than the other, it can bring one down or bring one up to where it is a constant output on the base portion to be sent up and out. That's what it is. It's nothing more than a common base transistor, and that's how it's able to combine the order wire with the mission traffic. So you're going to have 8.5 megahertz as well as one or the other mission traffic on it. We're going to run it through a diplexer. Where have you heard that from? Back in, what is it, Thursday was the last time. This one is made up of low pass and high pass filters, band pass filters, you name it, it's in there. And if you open one up, you'll see a lot of inductors and capacitors in there. That's for trying to get one signal out and the other one blocked, and vice versa on the other one. With this case, we are sending out the aggregate and our order wire out to the back of our baseband assembly. We are blocking the 70 megahertz IF from getting in on that line. We're also blocking our mission traffic and order wire from coming in on the 70 megahertz line. So you can see it has a dual purpose here. The idea is we're going to combine it and put it on one cable. If you take a look at the 2-foot cable when you get ready to plug it into the baseband or the RF assembly, take a look at it real quick. You'll notice that there's a whole bunch of pins and one what appears to be a very small RF cable in it. That's that cable. So we're going to run this out of the baseband assembly and use the 2-foot cable, unless you're going to use the 150-foot cable, and connect it to the RF assembly. Now this is what the RF assembly looks like. I'm going to blow it up. just so if I got to come back here, I can see it. You can see that we got the receiver and transmitter frequencies as well as another receiver frequency on the bottom left-hand side. We also have a meter. The reason why we have the meter is twofold. Number one, to see if I have the control voltages from the baseband unit, because that's where all the power comes from. And second, to see my receive signal level as well as my transmit power. So transmitter power is forward power. Our RSL, which is receive signal level, that's what we're receiving in. Both of those should be in the green for us to work. You'll go through it. Channel error light, that's when we get it out of the frequency range, and the summary alarm tells us if there's a problem with the actual RF assembly or the baseband assembly or both. Normally when both light up, it's the cable. Sometimes by snapping it into place, because I've seen that happen before. There's a little click on the cable that if you don't fill that click in, you're probably going to get a summary alarm on both the baseband assembly and the RF assembly. So we're going to bring that baseband signal in. It's going to have order wire, and it's going to have our aggregate from the multiplexer, whether it's pseudo NRZ or if it is CDI. We're going to go through diplexer again. As you well notice, this one is set up to pass, the same thing. It's going to let our aggregate as well as our order wire come into one place, but it's going to block it on the receive side, and vice versa. So we're going to get this signal in, route it to the first place, which is an amplifier. Why? Because think about it. A 2-foot cable doesn't need as much amplification as a 150-foot, does it? So you got to have an amplifier there. But there's more to that particular amplifier. It's called a compression amplifier. You're going, okay, compress amplification. It always amplifies. Always. However, the compression part is in there when you're using probably the 2-foot cable. And the idea is we want to keep that signal coming into our modulation section constant. Where have you heard that? So anytime you see a triangle, normally that indicates an amplifier. We're going to go to something called a transmit encoder. Well, a transmit encoder is this. Right there, those thumb wheels, that's what it is. Those thumb wheels are going to send out a BCD signal. Anybody know what BCD stands for? Nobody? Anybody? No one knows what BCD means? Okay. Binary coded decimal. In other words, behind that set of thumb wheels, when you turn them, you are toggling transistors on and off to give 1 and 0s out to send to our phase lock loop to tell us what we need to be on. That's what it is. 1s and 0s, binary coded decimal. It's either a 1 or a 0. Normally, it's in relationship to a transistor being turned on or turned off. Now, this part right here, the data switch, is extremely important in one switch on that front panel. And it's on the baseband panel. It's called the operate or standby switch. Operate meaning we're transmitting. Standby means that we're doing loop back and there is nothing coming out of the antenna. We are in the operate phase. I think that's a good idea. I think I need to put that at the front end. Let everybody know that we're in the operate. Switch is in operate. This data switch is controlled by the standby operate switch. In operate, it's going to let the transmit encoder go through and tell the PLL as well as the VCO what they need to produce, what frequency needs to be there. Now, you'll notice that I've got this marked with modulation. This is where modulation takes place. It's a voltage controlled oscillator. It's also a discriminator. This discriminator is going to take our aggregate as well as our order wire, and it's going to convert it into in this case is going to be our IF. So we're taking it, modulating it into an FM signal, frequency modulation signal, at the VCO here. Now, if you were to take a look at phase lock loop, look at the VCO that I've got circled in blue. Look above it, and it says divider. Follow the bold line. You'll see it goes into another divider. Then it goes into PLL. And then it comes down, back onto the blue line, and then back into the VCO. Let me try to explain to you how phase lock loop works in this scenario. The encoder tells the data, goes through the data, through the data switch to the phase lock loop. The phase lock loop is going to generate a voltage to control the voltage controlled oscillator. The voltage controlled oscillator is going to ramp up its frequency. The two dividers that you see is taking the frequency and bringing it down to where it can tell the phase lock loop when it makes the comparison from the encoder to the comparison of the VCO's output frequency. Once it senses that, okay, I either need to go higher or lower, it's going to send a voltage to the voltage controlled oscillator and say, you need to produce more frequency or less frequency. That's how the phase lock loop works. Now, when you get everything going just right, there's going to be a null voltage being sent out of the phase lock loop saying, hey, everything's good. So voltage controlled oscillators stay there. So that's how that phase lock loop works. It's going to compare what the encoder is sending it versus what the voltage controlled oscillator is sending. So it compares those two and it makes adjustment to control the voltage controlled oscillator. On top of that, that's where modulation takes place too. So it's a dual function item. Normally it's a common emitter transistor, but it's fabricated where it has 4 leads on it. It's been a long time since I've looked that up, so take it with a grain of salt. So when we come out of the VCO, it is not the operating frequency. It's intermediate frequency. With that intermediate frequency, it's going to be somewhere in that vicinity of 7.2 to 7.625 gigahertz. Yeah, it's not the operating frequency. That is our intermediate frequency. So again, the phase lock loop is going to tell what the VCO needs to produce. We get to the next stage, which is the multiplier. This is your up converter. Wow, sounds like your basic radio, doesn't it? Well, we had modulation going from baseband to IF. Now we're going from IF to RF. Oh, wait a minute, Mr. Mary, you said that that triangle is an amplifier. Yes, it is. Well, how does it multiply? Oh, I love this part. The idea behind amplifiers is when you increase the gain of a signal, you generate something called harmonics. Our first order harmonic is going to be 7.2 upwards to 6.25 gigahertz. Our second harmonic is going to be somewhere in the vicinity of 14.4 to 15.25 gigahertz. Get the picture now? Well, the idea here is FM is probably one of the easiest signals to generate harmonics with. So we're going to take that second set of harmonics and give you the information necessary. In other words, it doubles the input. And I've dealt with radios since 1987 up, and I've seen radios where they take the second harmonic. I've seen radios where they take the fourth harmonic. After the fourth harmonic, it's pretty weak. So after the fourth harmonic, we don't even worry about it. So either the second or the fourth. This one, we're going to take the second harmonic and we're going to run it through a bandpass filter. This is where we're going to select anywhere between the 14.4 to the 15.25 and just get everything else weeded out. Well, after we do the bandpass filter, we're going to amplify it. Wow, we just did the 3 steps of the basic radio here. We've went from baseband to IF, which is modulate, went IF to RF, which is up convert, and now RF amplification. Those are your 3 stages. See how you can apply this to just about anything here? So with this, it's called a field effect transistor. That's what the FET stands for. Normally these things are either 6 or 8 leads off of that transistor. Yeah, they pack a huge amount of power in it. Well, with our amplification, we're going to have anything upwards of, I think it's 316 milliwatts and 25 dBm. Use those interchangeably. The next part of this story is, oh look, the branch assembly. So now we've done the 3 things, transmit baseband to the distant end. Now we're running it through the branch assembly. This is only transmit now. We're going to have an isolator, a filter, a circulator, and another circulator. Let's take a look at each one of them. Gosh darn it. Isolator. We're going to let the RF go out, but we're not going to let any RF come back in. The idea here is I don't need it to get back in my electronics, especially if it's got a high VSWR on it. We're going to run it through a harmonic filter. Just like what I said before, anytime we amplify, we're going to generate harmonics. In our case, we're going to eliminate those harmonics as well as noise that goes along with it. We're going to run it through a circulator. This is a 3-port circulator, but there is a problem here. We do have 3 ports connected to it, but you'll notice that one of those ports is disconnected right now. You're going, okay, I don't understand. Well, take a look, go up, and you'll see what looks to be like a pre-selector filter. Go off to the right side, you'll hit an attenuator. And then you go up and you'll see a little node. Well, that node is not connected to anything, is it? So realistically, it has nowhere to go but out one way through a switch. This is a transmit standby relay. In that case, we've got it in operate, so we're going to link it to the antenna. Now you see that we got a 3-port circulator here. This one is operating all the time. So it's going to route the transmit through and let the receive signal go into the up path. At the same time is preventing the RF in transmit from going onto the receive path. Kind of wild, ain't it? And then out the antenna, through the dish, through the coupler, waveguide, and then to the distant end. Pretty wicked, huh? Any questions?
No, sir.
Overwhelmed?
Yes, sir.
Yes, sir.
Okay. Remember now, you can ask questions. Had a couple of you asked this past weekend, so that's a good thing. So please, I encourage you to ask. All right, let's switch gears. Anybody have a question? All right.
No, sir.
We're going to look at the receive signal flow. Again, this is still the standby operate switch is in the standby position. And you're going, I still don't understand. Let me go back here. Get back to this device right here. This position, take a look at your order wire LRU. Where's your order wire LRU? Far left-hand side. You can see it right below the meter. It says OW, order wire. Go up. You'll get past the meter switches where it says receiver baseband, transmit baseband, AC 12 volts. There's a switch right above it. It says standby and operate. That's the switch I'm referencing to. In our case, we've got it in operate. So the first place we're going to go to is we're taking the receive signal, we follow it through, we go through a circulator, through a standby switch, a pre-selector, and an isolator. Again, this is the receive branch assembly. None of this, as well as the transmit, is powered. Works by themselves. So let's take a look. So the circulator is going to let the transmit RF go out the antenna, and prevent the transmit side from getting into the receive side. Now the receive signal is going to come into the receive side and keep everything else out. We're going to go through this standby operate relay. Again, it's controlled by that standby operate switch. It is in the operate position by looking at this. Then we're going to go through that pre-selector filter. Now, where's the pre-selector filter on the front panel? Well, if you take a look at it, the pre-selector filter, left-hand side, it says receive frequency. You adjust this dial to the frequency that you want to be on. That dial is very important. If you don't adjust it to your receive frequency, there's a very good possibility when you go from standby to operate, it will not work. So you'll be standing there going, I don't understand. So again, passes what we want, the receive frequency. You'll notice that the word pre-selector is on it. In other words, we're selecting a small range within the frequency spectrum that we want and rejecting everything else. We're going to go through an isolator. In other words, we're going to let the receive signal go into our receive side of the house where all the electronics is and prevent anything from where the mixer and stuff like that is from getting out, because we do not want it to interfere with anything else. Again, it's a one-way path. So here's the first stage of a basic radio. Remember, we're going to recover the baseband. First stage of recovery is we need to have a selectivity / sensitivity. So our sensitivity is going to be relationship to the RF amplification. So RF amplification, we're going to have down convert, and the next one should be demodulation from IF to baseband. So in this little section right here, we have an amplifier. That's your LNA, low noise amplifier. This is going to give us enough gain where we can use it to mix with the signal to get our couple signals out of there. This is your down converter. And the reason why it's got a bunch of these in place is not to confuse everybody, but the first place I'm going to show you is where the 70 megahertz is made, but you got to clean up everything else afterwards. Let's take a look at this next device here. It's called an image reject mixer. If you look at the receiver encoder far right hand side, You'll see that it's tied to the receive synthesizer, which is your phase lock loop, the VCO, and that. It is identical to our transmit synthesizer. The difference is the encoder tells it what to do. Now, with this phase lock loop, of course, we're going to lock this frequency in place. But au contraire, if your receive signal is at, let's say, 15 megahertz, what should your VCO coming into the mixer be? Anybody have an idea? What would be the frequency? Would it be the same as your receive signal level or receive signal?
Yes, sir.
How's it going to mix?
No.
If you got, let's say, 15 megahertz, it's coming in, that's your receive signal, and you put 15, not megahertz, sorry, gigahertz, and you told the encoder, I need 15 gigahertz, that mixer has one word relationship to it. It's called heterodyning. Okay? Now, the last time I took a look at heterodyning meant that you're going to get the two originals out and you're going to get the sum and the difference. Well, if you have both of them the same frequency, are you going to get the sum and difference out? Answer is no. So with this particular one, it's going to be either 70 megahertz above the receive signal or 70 megahertz below. It doesn't say plainly what it will be. And my suspicion is there's a certain area where it's going to be above and there's going to be a certain area where it's going to be below. It is very possible that it may all be below or all be above. The idea here is when we mix those two together, we get a sum and a difference. So let's just pretend I got 15 gigahertz being selected, that's the frequency I want. That means that VCO's got to produce 70 megahertz. In this case, I'll go with above. That way it makes it easier for us. So it'll be 15 gigahertz receive signal and 15.070 gigahertz coming into the mixer from the VCO. With that in mind, heterodyning comes into play. So you mix the signals, you get the two originals, which would be the 15 gigahertz, the 15, okay, sorry about that. I don't know why Discord, well, let me take a look real quick. 1, 2, 3, 4. We have 4 sets on Discord right now, so that's probably the reason why it's choppy. Is it any better now?
Yes, sir. It's just like sometimes it just glitches out really quickly.
Okay. Yeah, Discord is really struggling because, again, we're not the only squadron that's doing this. There's a couple other squadrons that are doing this on the base, so they're using Discord. Now think about it. I talked to my nephew a couple weeks ago, and they're doing it at, what's the base in, I think it's Oklahoma. It's above Texas. Wichita Falls. What's the name of it? Shepherd. They're doing it at Shepherd. So you see how many people are doing with Discord? So I suspect that there's going to be some issues with it. So hopefully it'll clear up for us. All right. So with the mixer, we're going to get the 15 gig, the 15.07 gig. We're going to get the difference, which is 70 megahertz. We're going to get the sum, which is 30.07 gig. So those are the 4 that are coming out. But our 70 megahertz is made right here. Why? Because we want that 70 megahertz. How do we get it? All right. Well, we're going to have to amplify it because we did manipulate the signal. The idea is when we start filtering it, I need to have it strong enough to get past the filters. With those 4 signals, they need to be what I call stepped up in amplification to prevent a whole lot of noise being generated. With this in mind, we got 4 frequencies coming into the second amplifier, and this is where we block everything else. This is a bandpass filter. It is centered on 70 megahertz, and if you read the tech order, it will say 70 megahertz plus or minus 10 megahertz. What does that mean? Well, the frequency range this has is from 60 megahertz to 80 megahertz. Get it? The plus and the minus. So this is where everything gets cleaned up. That's the reason why I called it the up converter, or down converter, excuse me. Once we get that out, it's going to determine what our AGC is. And remember REGO? The whole idea behind REGO is to keep our output constant. We're going to then go through a diplexer. In this case, we prevent the order wire and the aggregate from getting on the 70 megahertz line, but at the same time, we are able to let the 70 megahertz go out onto the RF cable there. We're going to run it out of the back of the RF assembly into the back of the baseband assembly. Now, if you hadn't noticed, we are on pages 6 and 7 on our C's and D's. Highly suggest that you go through these, because it'll help you out. Now, I'm going to show you something on this last one. What is an LRU? Well, an LRU is a line replaceable unit. Well, how do you identify it on the C's and D's? Well, let's take a look at the top box here where it has a dotted line all the way around. And you'll see that we have a 1A1, A2 microwave LRU. That's an LRU. Well, what's over here in the bottom, the middle left, you'll see that we have a transmitter synthesizer, and it says the 1A1, A4 synthesizer LRU. Is anybody having problems locating it? Please speak now, forever hold your peace. Here, I'll even... Oops. How about that? You see it? Let's do this. Outline. Right? Outline. Okay, so you can see that. That's where one of them is. That's the synthesizer LRU. And the one I was talking about earlier is right here with the microwave LRU. Then we have what's called the controlled distribution LRU up here. Again, there's more to it than meets the eye. The one that we just covered are the 2 LRUs with a portion of the controlled distribution LRU. Let's do this. Copy, paste. I don't want to do that. There you go. So those are identifying your LRUs. There is a possibility you might have to identify one of them. Okay, so we have the baseband assembly that we have got from our receive signal from the RF assembly. We're going to come through the back of it on that 2-foot or 150-foot cable. We're going to go through a diplexer, and then we're going to hit a cable AGC. This is specific that if you're using the 150-foot, there's probably going to be some amplification in there. If you use a 2-foot, there's probably going to be very little amplification. Again, that compression amplifier falls into place. We're going to go through something called an IF demodulator. This is where we start to see the IF to baseband. Anytime that you see the last portion here, click this. Come on. Save this just to be on the safe side here. This is where demodulation takes place. Now, notice that I got a couple of these. Realistically, demodulation happens in the IF demodulator. When it comes out, there's a slight problem. I don't want the 8.5 megahertz to be on the aggregate, and I don't want the aggregate to be on the 8.5 megahertz. So we have to separate them. That's the reason why I divided it up a little bit more, or made it elongated. So when we go through and hit the low pass filter, it's going to pass mission traffic. Now, if you have any ideas about how filters work, it is not cut and dried. It is not going to pass completely the mission traffic. There's a very good chance that some of that 8.5 megahertz order wire is going to get through. It doesn't happen in the subcarrier notch filter. This is where the 8.5 gets completely taken out of it. It's only going to let mission traffic go through. So you go, well, why have the low pass filter? Well, there is a very good chance that that 70 megahertz may have made it through the IFD modulator as a residual, because of the components are very close together, so it may be bleeding over onto another component. By using the low pass filter, we're going to take anything from the distant end and weed it out. That's the reason why, the main reason of the low pass filter. Of course, electronics is kind of one of those wonky things that you got to figure out. Oh, okay, this is the reason why it has. Most components that are out there has a double, if not a triple duty with it. So we have a subcarrier notch. This is where our aggregate gets through, either the pseudo NRZ or the CDI. The order wire does not go through. This FOGM interface, this is a switch on the front panel of our baseband assembly. Let's take a look. Did I pass it? I sure did. Here's our baseband. If you take a look at the receiver LRU, which is next to the power, and look up past the attenuator, it is the last switch at the top. You'll see GM and FO. GM meaning group modem, FO meaning fiber optic. There you go. Even shows you everything that you need to know about NRZ. Remember now, anytime we say NRZ, it's assumed that we know that we're talking about the pseudo NRZ. Group modem, CDI. It's been my experience that we've done nothing but CDI since using these, since using the tester. I have not used the pseudo NRZ, mainly because we don't have the fiber optic connectors. I'm sure it's been done out there. And then the attenuator, this one's only 10 dB of attenuation, not 30. Why? Because when you get it out over the airways, it's not going to be that strong. Again, this is utilize your front meter to check the attenuation. I think I've only had to use it twice in getting the attenuation down and not up. So the next one we're going to go through is something called order wire. So that concludes our receive signal path. Now, where does this receive go out to? It goes to the multiplexer. That's part of that Canon plug or the fiber optic. So order wire. What is order wire? Well, order wire is that auxiliary channel we talked about in the earlier stages, I think of 4 alpha or bravo, where we described what our order wire was. So the object of water wire is, in order for us to have our own channel, is mainly because of the troubleshooting that we have to do. First, we got to make comm with ourselves, and then second, if there's something wrong with a user or something like that, we can talk to the dissonant and see what kind of issues that they're having. You'll notice that we have a lot of bold lines on. You can either use the baseband unit, either transmit or receive, just to take a look at this. Again, this is your electronic C's and D's. You can take a look, as well as the tech order. Now, if you look at the middle right, you will see a speaker, or what appears to be a speaker. Right above it is a connector. This is for a handset. Handset always goes to the baseband. Headset goes to the RF assembly. I'm going to warn you ahead of time. Whatever you do, do not put the headset on in the middle of checking your unit out. And you're going, why? We're going to have to talk to each other. Well, that's true. But wait until after you do the test tone checks. Why? Because if you got those headphones on and you turn the test tone on, you're probably going to be screaming at your partner. Why? Because it's pretty loud. All right, Bridges is going to the restroom. Let's take 5 real quick. From 9:47 is what I got to 9:52. All right, quick. Let's go. Have you guys heard what happened, I think, Friday?
No, sir.
It appears that they've had an increase in COVID cases, so they are, keeping everybody locked down. In fact, the instructors and that have went from, I guess, back to Charlie for health protection.
Yes, sir. So, sir, we have the question about blues tomorrow. If we are to wear blues tomorrow, do those who have lab have to wear blues to the lab?
From what I understand, no.
Oh, yes, sir. Because I asked the IS, and the IS told me to ask you.
Me?
So I think that's your discretion.
Let's put it this way. You're going to be carrying a lot of heavy objects, and the last thing you want to do is be wearing blues setting this stuff up, because it is dirty.
All right, yes, sir. So if we have lab tomorrow, we won't wear blues. Perfect. Thank you, sir.
Yeah, that's that's always. Now I could see the NSM lab wearing blues. You're just punching numbers, but you come right down to it, you get back behind those cases, there's some voltages back there, so I'm not sure I would be wanting to wear any metal objects. So, throughout my life with the Air Force, I very rarely wore blues. Okay, good, Bridges.
That's what we were told too, sir. And then we came to Keesler. And
Well,
then we blues all the time. So.
Yeah, well, it's AETC, and they want you to be familiar with wearing blues. If you're a back office person, you're probably going to be wearing blues a lot. If you're maintenance, yeah, no. If you're doing a lot of stuff outside, the chances of you wearing blues are very slim to none. Now, I have seen where the supervisors would have to wear blues because they weren't out in the field. But every place I have been, it wasn't until I got to Keesler before I started wearing blues on a consistent basis. And that was normally, oh geez, once every 2 or 3 months, we would have to wear blues. So,
Yes,
I
sir.
think the last time my base had a blues day, it was like 3 years ago. It's a guard base though, so.
yeah, it's true.
Sir, real quick, can you just give me a quick rundown of the CID explanation, like before everyone gets back, or do we not have time?
CID. Okay, help me out here. It's been a while. What's the CID mean?
Conditioned diphase.
Oh, CDI.
Sorry, yes, sir. Yeah,
I'm going, okay, it's been a while since I've heard that term CID. You know, anyway, conditioned diphase relies on transitions instead of voltages for being a high and a low. With transitions for logic 1, we only want 1 in that clock cycle. For a logic 0, we're going to have 2 transitions. And it doesn't matter if it goes up and then down or down and then up, as long as we get 2 transitions. Logic zeros are in sync with the clock cycle. Logic ones do not have to be in sync with the clock cycle. It's an unusual occurrence when they're out of sync, but that's the reason why CDI is clocking, self-clocking, is because of the distant end as well as the front end can determine what's going to happen within that clock cycle.
Okay, yes, sir. I appreciate that.
Sure. I hope that clears it up.
Yes, sir. It does.
All right, so Chung's here. Hamilton, you here?
Yes, sir.
Okay, Hancock, right in the chat. Londono?
Yes, sir.
Okay. Bridges?
Yes, sir.
And Hubbard?
Yes, sir.
Malin?
Yes, sir.
Hey, Matei?
Here, sir.
Good. Richard?
Yes, sir.
And Dran?
Yes, sir.
And Zellers.
Yes, sir.
You guys
All right.
I can be heard now?
Yeah, you sound fine. All right, with order wire, left off with the connector. If you follow that connector through what's called the order wire LRU, 1A2, A2, come on. How hard? Can't believe I did that. Try this again. There we go. That's your order wire LRU, and the place that I am looking at is here. Picked it. Come on. Jeez. So that's the connector. We come into LRU. We follow the bold lines down. We're going to come into something called a transmitter generator. Transmitter subcarrier generator. This is 8.5 megahertz. You are being modulated at this point in FM. So the transmitter subcarrier generator is an FM signal, then it sends over to the summing buffer amplifier to combine with excuse me, to combine with your aggregate. Aggregate being either CDI or pseudo NRZ. And if you follow it through, then you're going to go out to the RF assembly, and then it's going to get modulated onto the carrier at the 14.4 to 15.25. So it's basically what the reason why they call it a sub carrier is it's not in cahoots with being a real carrier. If it was a real carrier, it would be carrying the aggregate. But since we have some issues with, if you take a look at it, the FM versus digital, you don't have too much of an issue between the two. So by keeping them one in an FM signal and the other one being a digital signal, there's no interference between the two. And then, of course, when it comes back around, when we got to demodulate it, we take a look at the IFD modulator in the top section with the receiver baseband unit, where you see IFD modulator and then the low pass filter, the subcarrier notch, and that. Well, take a look at where that bold line is. And again, you've got the aggregate and your order wire coming in, but the 8.5 subcarrier demodulator is going to only demodulate that FM section. It's not going to demodulate the aggregate. So we take that signal, run it into the order wire intercom, and then out the handset. So you are now an analog / signal. And by you talking into the mic or listening to it, there's where your information is. So that's one state. So let's take a look at it. And again, your front panel, your switch right above the meter where it says standby operate next to the summary alarm will be in the either operate or standby position. It will not matter. There you go. Order wire assembly. You have transmitter subcarrier on both ends, one to modulate it, one to demodulate it, depending on what you're doing. There is a little section here where we call the test tone oscillator. It can be modulated or demodulated, especially in the standby mode. If you have this in operate and you use the test tone oscillator, you'll probably end up getting the dissonant cussing you out. Why? Because someone had the headset on and they got a blast of that test tone oscillator. Not a good thing. Not a good thing. Also, when we talk about the test tone detector, let's go up here back. The test tone detector. All right, where is test tone to begin with? Let's look at the order wire. Tran, I think your mic is keyed. Yeah, your mic is keyed there. So,
It is, sir?
yeah, it is. Okay, now you unkeyed it. Good. Okay, your order wire, LRU, take a look at that. And what you want to do is in the middle of the panel, you will see test tone with a light next to it. You'll see the switch. It'll say baseband, off, order wire. When you are in either one of those, you will see, take a look at the LRUs, the two middle LRUs, one transmitter, one receiver. You'll see a white light that will say next to it T/T. That's for test tone. When you have that either in the baseband or the order wire assembly, those lights on the transmitter, and take a look at the receiver, it also has a white light that says T/T. That's where those lights will illuminate. When you put it in the off position, they should de-illuminate. Kind of sounds like, what is it, Demolition Man? Illuminate, de-illuminate. So that's what the test tone detector will do. When we look at standby loopback, we are looking at the transmit, or the RF assembly is the best way to look at it. Now, what actually had to happen? Well, the first thing is we have put the standby operate switch in the standby position. What does that mean? Well, if you take a look at the data switch here, which is the middle of the page, far left, you'll see the transmitter encoder is not bolden, but the data switch is. And all of a sudden you can see all of the transmit section bold as well as the receive, not like it was when we were talking separately from transmit and receive. We either had the transmit path bold or the receive path bold. This one is including both. Well, why in the heck are we doing that? When you put the standby operate switch in the standby position, what you have just done is you have told this data switch to take the transmit encoder out of line. Okay. But it puts the receive encoder in line. Why is that? Well, if we are in operate, that means my transmit frequency has to be 200 megahertz away from my receive frequency. It doesn't make any sense to try to do a loop back with a difference in frequency. It won't work. It will not work. So what they did is they came up with this idea, we'll put a data switch in here, so when we put it in standby, I put the receive frequency on the transmit line, so when it comes back around, I can actually receive it. I can actually modulate and demodulate. Hence, that's the reason why you put the test tone in, or you can either talk on your own voice, talk to each other. So you're actually modulating and demodulating. So that's the reason why we point this out. That data switch is very important when it comes to operate or standby. Operate, it puts the transmitter encoder in line. With standby, it puts the receive encoder in line so it can do the loop back. Start to see it now? So that data switch is very important when it comes to putting it in standby mode, and that's how you're going to do all your checks starting tomorrow. Again, that standby operate relay, when you take a look at those two, you're going, well, where the heck are they? Let me show you. Far right hand side in the microwave LRU, you will see at the bottom of that dotted line, you will see a transmit standby relay 2, and then go above where the standby operate relay number 1 is next to the pre-selector filter. So those are your two relays. Now, the other part of that story is when you're routing the transmit through, it disconnects from the antenna and it runs it through a dummy load. It also takes that signal, runs it through a pre-selector and an attenuator to bring the signal down even more, because you don't want 316 milliwatts coming back in on the receive section, because it's going to be expecting something a whole heck of a lot weaker. If it was 316 milliwatts, you're probably going to saturate the front end and destroy your receiver. So that's the reason why you see a dummy load in there and an attenuator. Then when you route that signal through to the pre-selector filter and then into the receive section, there you go. It's at a level that they can deal with. And that's the reason that we have the switch in there. So not only does it control the data switch, but it also controls the routing. It cuts the antenna off in standby. When you guys are in there getting ready to fire up, in other words, plug it in and turn the pisser on, the first thing it tells you to do is make sure your standby operate switch is in the standby position. If it isn't, then you'll be instantly transmitting, and that's not a good thing. It's especially if you're right in front of it, because a blast of RF can get warm. Now, granted, you're going to have to stand in front of it for a couple minutes, but why take the chance? I think the safety for the tisser is 5 feet in front of the dish. You can be off to the side. I really wouldn't be off to the side too much. You know, if you're like a foot away from it, I would be kind of reluctant. So I think the warning says 5 feet in front of the dish. So we've gone over purpose, operational characteristic, types of traffic, equipment, and signal flow. Any questions? Everybody's mind numb right now, going, oh my gosh, this is crazy. No? No one gets it. Everybody says no. Everybody gets it. Yes, no. Maybe what? Feedback.
I'm gonna go with numb.
Yes, I'll go with that one too.
Yeah, I think I just have to look over the C's and D's a couple times. It was kind of hard to follow just because I'm on one screen, so I can't like pull up my electronic C's and D's
Okay.
and listen to the lecture at the same time. So if I go through it over again, I'm sure I'll have some questions.
Well, you also have the recording,
Yes, sir.
which is a good thing. I actually pressed record. Getting old sucks. All right. Did I go over 5 alpha? Do you remember?
No, you haven't.
I did?
No, sir.
All right. Tells me it's the same. You know. I don't know what the heck's wrong with this PowerPoint, but I've got like 6 PowerPoint slides that work just fine when I come to OBS, and then the last 3 don't. I got to modify. So this one says 5 alpha, identify basic facts and state general principles associated with controls and indicators of the tropospheric satellite support radio. Realistically, we've already gone over it because when I took you through the tech order in chapter 4, tells you everything you need to know about it. You're going, we did? Yeah, hang on just a sec. And once again, I can move just a little bit. And remember these? First of all, it gives you like the RF assembly.
I remember that, sir.
There you go. This is table 4-1 and 4-2 on pages 4-3, 4, and 5. Tells you anything and everything you need to know about the front panel of the baseband assembly and the RF assembly. That's pretty much what this is all about. It's just going through that table. Any questions on that? Again, you're probably going to have to go through the stuff and do your research. Wow. No questions, huh? Everybody's afraid to ask one because they don't want to be the first, right? You probably have a ton of questions, so again, if you want to message me, please be my guest. Again, I'm on Discord a lot. So here's what we're going to do. We're going to end it here. We have pretty much covered everything in lecture. We're going to do homework. Let's, anybody have any objection to 1 o'clock for homework and going over?
No,
'Cause
sir.
someone can say, no, I got an objection, or yes, I got an objection, whatever it is. But the reason why I chose 1 o'clock is you got an hour before you go to lunch, you got after lunch, so it should be enough time to get whatever's left. Again, some of you have already turned in most of your homework, so an hour after we get done with homework, that way it'll give you enough time to clear it up and gives you enough time to, you know, if you got some Discord issues in taking a photograph and sending it to me, or copying it and pasting it in there, there you go. So then let's do this. 1 o'clock then. We'll go over everything from 3 alpha to 5 alpha. And then at whatever time we get done, I'll give you an hour and you'll turn it in to me. All right?
Yes, sir.
Yes, sir.
Yes, sir.
All right. We'll see you then. 1 o'clock. Be there, be square.
Sir, I do have a question. if you
Sure.
don't mind. So for review questions for alpha,
Mm-hmm.
the number 4,
Okay.
the question is, what frequency does an IF repeater perform the majority of the amplification? I'm not really sure what to put there.
Hang on just a minute. Let me blank this out real quick and go to my handy dandy list so I can make sure I'm leading you in the correct path here. What question was it? 4 on 4 alpha?
Number 4.
On 4 alpha.
Yes, sir.
Okay. All right. Look in your electronic C's and D's. It should be page 2, and it shows an IF repeater.
Do you mean 3 alpha?
No, it says 4
No,
alpha.
4
At what
alpha.
frequency does an IF repeater perform the majority of the amplification?
70 megahertz?
Yep, exactly.
Okay.
Yeah, because
Thank you.
if you know, most of 4A is coming from not only a study guide workbook, but part of the C's and D's. So you have to look on your C's and D's for that one.
Okay. Thank you.
You're welcome. Anything else? All right, we'll see you at 1 o'clock then. Guys, have a
Sure.
good lunch.
As well.
All right.
You as well, sir. Thank you.